for fur for insulation in small, ground-dwelling predatory dinosaurs.
Fossils have revealed the dinosaurs' armor and shown evidence of the first feathers on Earth. But in 2007, paleontologist Phil Manning was invited to study an incredible Triceratops fossil found in Wyoming.
I was contacted by a paleontologist, Peter Larson, who discovered a Triceratops. We know that this particular fossil is of a Triceratops because we have the beautiful three-horned skull at one end of the fossil.
Triceratops was the largest of the horned dinosaurs, measuring approximately 25 feet long and a whopping 10 feet in height. What made this find so special was something that had never been seen before: dinosaur skin.
And it was only when they started removing large tracts of the sandstone which was encasing this beautiful fossil that they discovered these large tracts of skin impressions, or what might have actual skin, preserved on this amazing fossil.
Manning's excitement about this find's importance is palpable.
It's not like finding a few disjointed sentences which are hard to piece together to work out what they actually mean. Here we've got a full-blown paragraph, if not a whole chapter, which we can gently thumb through and understand so much about this particular animal's skin.
Powering up the electron microscope, Manning is about to take his first step toward cracking the skin sample's code. The view is an unprecedented trip back through time.
What you're actually looking at on the screen here is the surface of our fossilized skin. That's beautiful. You're looking at the surface of some Triceratops skin that's a little over 65 million years old, and that no one's ever looked at it in this resolution before.
This microscope allows Manning to see what elements are present in the fossil.
Where we haven't got elements identified, I can actually use the software in this machine to help identify the specific element. We've got silica, oxygen, carbon is present. That could be some of the plant remains that we find within this environment.
Some of the elements present in the skin fossil suggest some tantalizing ideas.
Ooh, manganese. I like manganese. Manganese is important.
Elevated manganese levels may indicate that the skin was fossilized in colder than expected conditions. As the clues are pieced together, a new window into the Cretaceous environment begins to emerge. But the biggest surprise is on the outside of the animal. They discover an enormous variety in the size, shape, and texture of the scales on the skin.
They're not small scales. These are quite robust, tough-looking scales.
A new, clear picture of Triceratops comes into focus.
Now, looking at the types of scales that we see on the skin on this particular Triceratops indicates that it didn't have a soft spot on its backside.
Manning finds tough scales that would protect this creature from its harsh environment. But surprisingly, there is no bony ossification. This animal would have little defense against a T-Rex bite. Triceratops lived toward the end of the dinosaurs' incredible 160 million year reign on Earth. Scurrying beneath the beast's lumbering feet were a different kind of animal. Warm-blooded mammals whose adaptive skin would change in ways that would allow them to grow and dominate the world as the dinosaurs had before them. Mammals live for 160 million years in the shadow of the dinosaurs. They remain small and out of the way for a long time. But with the dinosaurs gone, there is new opportunity, and hundreds of new species evolve. And two amazing adaptations in skin ensure their survival almost anywhere.
Mammalian skin is different again from reptilian skin because mammals differ fundamentally in their physiological properties.
This physiological difference rests in the way the bodies regulate their temperatures. Reptiles are cold-blooded, so their body temperature depends on their surroundings. When it is cold, their body temperature dips. They become slow and sluggish. When it's warm, their body temperature rises. They are more active. Mammals, on the other hand, are warm-blooded. They maintain their own constant body temperature. This gives them an advantage in a climate with seasonal changes and extremes of hot and cold. But it also presents a challenge, because in the cold, warm-blooded mammals like us can freeze to death. As with the reptiles before, mammalian skin responds accordingly.
The skin of mammals has evolved over several million years to have certain properties, including marvelous outgrowths called hairs that protect the surface of the mammal and provide tremendous amounts of insulation.
Hair also guards against rubbing and abrasion, providing a lot of protection against routine wear and tear.
So as an animal's running through the forest or rolling on the grass or on the ground, it is completely protected.
The ancestors of mammals, sprawling reptilian creatures called synapsids, probably already had evolved hair. It is thought that hair began as a mutation on the skin, sprouting up in small spaces between the scales of creatures, like weeds in a brick path. A close-up look at a contemporary human hair reveals that while hair appears smooth, it's actually scaly, just like a reptile scale. It's why our hair can tease up and be tangled into a mess, and why it lies flat when combed in line with the scale's bias. Hair is formed in the lower dermal layer of skin and can easily regenerate. Mammals evolved a unique kind of skin, one that boosted its chances of survival. They now have a head start in exploring new terrains because their insulation enables them to travel long distances and adapt to different climates. But it's not just about staying warm. In some climates, it's about keeping cool. The elephant's tough skin and large barrel-shaped body retains a lot of heat,